You know, we always ask this huge question. What is the universe really made of? Like, at the absolute bottom level. Is the reality we see all around us smooth and connected? Or, if you could zoom in far enough, would it just dissolve into something else? We're about to dive into a pretty radical idea that could flip everything we think we know about space itself on its head.
Okay, so let's do a thought experiment. Imagine you could zoom in on a tiny little patch of what we call empty space. I mean, keep zooming. Way past an atom, smaller than a quark. What would you actually find there? Does reality just keep on being smooth and predictable, or does it all fall apart into something totally different? This isn't just some fun question to kick around. It's genuinely one of the biggest unsolved mysteries in all of physics.
All right, here's our game plan. We'll start with how we see space-time right now, then we'll see exactly where our best theories crash into each other, and after that, we're going to explore a wild new kind of geometry that might just be the answer.
So to really get a grip on where physics might be heading, we've got to understand where it is right now. And the thing is, our current view of the universe is basically split right down the middle between two theories that are both unbelievably successful, but also completely incompatible.
In one corner, you've got Einstein's General Relativity. This is the heavyweight champion of the big stuff. Planets, stars, galaxies, the whole cosmic dance. In its world, space-time is like this beautiful, smooth, stretchy fabric. But in the other corner, you have quantum mechanics, the undisputed ruler of the tiny, subatomic world. And down there, everything's quantized. It's lumpy. It comes in little packets. It's weird and probabilistic. So you see the problem, right? One says reality is smooth, the other says it's chunky. They can't both be right.
And look, this isn't just some friendly academic disagreement. The real trouble, the real fireworks, start when you try to describe places in the universe where both of these giants have to apply at the same time. Think about the heart of a black hole, or the very first instant of the Big Bang.
When you try to force them together, when you try to merge that smooth, continuous world of relativity with the lumpy, jumpy world of quantum mechanics, the math just breaks. It completely falls apart. The equations start spitting out nonsense answers like infinities and singularities. That's basically the universe holding up a giant sign that says, "Nope, wrong answer, you're missing a huge piece of the puzzle." We need a totally new way of thinking.
And this is where the story gets really interesting. A physicist and mathematician named Alain Connes stepped in with a solution that's both incredibly elegant and, let's be honest, deeply weird. He basically suggested that maybe the problem isn't our theories of physics, but our theory of space.
He developed this whole new mathematical world called non-commutative geometry. Now here's the radical idea at its heart. It says we should stop thinking about space as a collection of points, with coordinates like x, y, and z. Instead, NCG describes space using the language of algebra. And in this new algebraic universe, the order in which you do things is everything.
This quote really just nails the whole concept. Kahn's big idea is that space itself is an algebra, where the coordinates, the very directions of space, don't commute. And that one little twist might just be the secret sauce that finally allows us to unify gravity with all the other quantum forces of nature.
Okay, I know what you're thinking. That sounds super abstract. Non-commuting coordinates, what on earth does that actually mean? Let's use a super simple, everyday analogy to make this crystal clear.
All right, think about getting ready to go outside. You put on your hat, and then you put on your gloves. You get a result. Now, what if you do it the other way? Gloves first, then the hat. You get the exact same result, right? You're wearing both. The order doesn't matter one bit. Those actions commute.
But now, think about this. You put on your socks, then you put on your shoes. Works perfectly. But now, try to reverse the order. Put on your shoes, and then try to put your socks on over them. It's a complete disaster. It's ridiculous. The order is absolutely crucial. These actions do not commute. Non-commutative geometry proposes that at the most fundamental level of reality, space itself behaves more like putting on socks and shoes than a hat and gloves. The order you do things in fundamentally changes the outcome.
Okay, so that's a cool analogy, but how does this wild idea actually help us describe the real universe? Let's take a quick peek under the hood, conceptually. No scary equations, I promise, and see what's in this NCG toolkit.
So first off, instead of using our usual smooth geometric spaces, NCG uses something called operator algebras. Just think of it like this. Instead of fixed points in space, you have actions and observations. And get this, it measures distance not with a ruler, but with something called a Dirac spectrum, a concept that is quantum from the ground up, tied to the energy of particles.
And what's really amazing is that with this framework, you can take the entire standard model of particle physics, all the fundamental particles, all the forces, the whole shebang, and it all fits beautifully into a surprisingly simple two-part geometry.
And this is where the theory's power really becomes clear. In our current models, the Higgs boson, the particle that gives everything else mass, it kind of feels like it was tacked on at the end. But in non-commutative geometry, it's not an add-on at all. It just emerges. It pops out of the math naturally, as a kind of ripple or an inner fluctuation of this new algebraic fabric. It isn't just something the theory allows for, it's something the theory predicts.
Now, all of this sounds absolutely incredible, and honestly, it is. But like any theory that's really on the cutting edge of science, it's got a whole lot of promise, but also some very real challenges that it still needs to overcome.
The promise here is just huge. This could finally be the path to a theory of quantum gravity that doesn't just break down and give us those crazy infinities. It could be the thing that resolves paradoxes like singularities inside black holes. It even elegantly predicts why we have the exact number of particle families that we see in nature and not anymore. It even helps to untangle some really tricky knots in other advanced theories, like string theory.
But, and this is a pretty big but, there's a major hurdle. While this theory is beautiful and works great in simple flat spacetimes, getting it to work in the kind of curved, dynamic, warp spacetime that Einstein's general relativity describes, well, that's extremely difficult. This problem, which physicists call renormalization, is the main puzzle they're trying to solve right now. It's the key that needs to be turned for NCG to really become a true theory of everything.
So if this has totally piqued your interest and you want to dive even deeper, these are really the go-to resources. Alain Connes' own book is the definitive magisterial text, but be warned, it's pretty heavy going. If you want a more gentle on-ramp, Kalkali's Invitation is an absolutely excellent place to start to really explore these concepts.
So, after all of that, what's the big picture? Let's just zoom all the way back out for a second and think about the really profound, mind-bending implication of this whole idea.
The single most important takeaway is this. If a theory like this is correct, then our perception of space as this smooth, continuous thing we move around in, it's an illusion. A really, really convincing one, but an illusion nonetheless. At its most fundamental level, the universe might not be a place at all. It could just be a set of algebraic rules. And the space that we see and experience is just an emergent property of those rules playing out.
And that leaves us with one final, kind of unsettling thought. If the very stage on which all of reality plays out, space-time itself, is just an emergent property of something deeper and way more abstract, then what other fundamental parts of our reality are just shadows of a truer, stranger world that we haven't even really started to see yet?